Hello everyone, I am Deepak Paliwal. So today we will discuss about the theoretical strength of a material. Before study the actual deformation of material, first consider a material. First consider a material without any defect. Okay, suppose this is our material, and we know the material is made up of various atoms. So we are considering the two planes. Suppose this is my plane 1. Let me take the different color for the plane 2. This is our plane 2. I am showing the single row of a material. So this is the plane, this is the plane 2, this is the plane 1. So suppose for the deformation of the material, this let us consider the deformation of a material by translation of this atom, or translation of this atom over this translation of the atoms of the plane 2 over the plane 1, by what I want to say, by translation of atoms of plane 2 over plane 1, deformation is proceeding. Okay, so this is the first condition. So what would happen in the second condition? This was the my first plane. Okay, I am making this very rough diagram. Let me correct it first so that the atoms are at the equidistant positions. So this is the my plane 1. Okay, again my plane 2. Suppose the atom from this position is shifted to this position. Okay, so the from this initial position, the final position is this. Suppose this movement is x only, and the distance between the atoms initially was the distance between the initial atoms was let us consider the b, and interplanar distance, let's consider it as a. Okay, and theoretically it is observed that if I plot, like let me draw with some different color, the plot between the shear strength or the shear stress versus displacement of atom is somewhere is like this. So this is not any function. This is like a very weird type of function. The movement of atom from this position to this position, or rather I should say the from this position to this position. So this is the relationship between the shear strength or the shear stress and displacement. If we approximate this relation with the help of a sine function, by considering the sine function, obviously this is not very well fitted by the sine function, but we are assuming it is acting as a sine function. So we can write our tau value, the shear stress is equal to tau m sine 2 pi x by b. We know the b is the distance between the two atoms when there was no deformation in the material. X is the distance traveled by the atoms of the plane 2 over the plane 1. Okay, tau m is the amplitude of the sine function. Now as the displacement is very small, we can say the displacement is very small. That means x is small. That means x is very low. The Hooke's law is valid here. So we can write our equation tau is equal to shear strain. This is the shear stress. This is the modulus. This is bulk modulus, and this is the shear strain epsilon, or I should write like that, let me represent with the conventional notation, that is gamma. So here gamma I can write is like that. Here we can say our gamma is like this. The x is displacement and a is our distance, so the gamma is like this. So we can put here again, gamma is x by a, and we know the a is the interplanar distance. So by putting this value here, x by a, now from the, let me call it as equation 1, this is the equation 2. From 1, what we can say, like x by b, where the x is the displacement of atom of plane 2 over the plane 1, and the b is the distance between the atoms when there was no deformation. Suppose this ratio is very small, then the sine theta becomes the theta only. So from 1 we can put, let me change some color here, let us have pink one. So now if I am putting the value tau is equal to tau maximum, or the amplitude of the sine function, 2 pi x by b. Now from 2, tau is equal to what? Tau is equal to, we have calculated gx by a. Now putting this value, we are putting this value is equal to tau maximum 2 pi x by b. Okay, so we can easily cancel the x with x. So now tau m becomes g b by 2 pi a. Now we have this equation. Let me write with some other color. Tau m is equal to g by 2 pi b by a. We know the b is the distance between the atoms and a is the interplanar spacing. Okay, let's consider b is equal to a. Okay, so the distance between the atom and interplanar distance becomes equal. So approximately tau m becomes the g by 2 pi. Okay, so the g for the metals in the range of like 20 to 120 GPa, and consider this factor 2 pi approximately 6. So now let me put the value like 120 GPa, rather this is 150 GPa. So 120 GPa I am taking and taking the 6 as factor. So if I am dividing, this is like 20 GPa. So the observed value of a single crystal material strength in the order of around 10 MPa, or we can say the strength of a material, or a strength of a material or single crystal in the order of MPa. But here we have having a theoretical strength in the material in the order of GPa. So why this kind of discrepancy inside the material? Like the theoretical calculation showing in order of GPa, but our practical experimentation showing in the MPa. So the what is the effect, or the what is the reason behind of that much very low practical strength in the material as compared to the theoretical calculation? So that we will find out in our next lecture. What is the reason of this theoretical strength is not being achieved by the material in the practical scenario. Till then, thank you, and thank you for watching my video. If you liking this video or any content of this series, if you find useful, please share with your friends, and please give us a thumbs up, which give us motivation to make more and more video, and to give more time and devotion towards this video, so that more and more people can understand in the very easy language. Thank you for the watching.